I want to define g of 3 in a way that extends g of x equals x squared minus 9 over x minus 3 to be continuous at x equals 3. By definition, it's going to be continuous at x equals 3 if the limit as x approaches 3 of g of x is going to equal g of 3. So let's look at what g of x is. G of x is x squared minus 9 over x minus 3. And this we can simplify to, well, x squared minus 9 will be x minus 3 times x plus 3 over x minus 3. The x minus 3's are going to cancel. And if I plug in 3 for x, I get 6. And this has to equal g of 3 in order for g to be continuous at x equals 3. So we're going to define g of 3 to equal 6. And now g of x is going to be continuous. So you can, if you want, you can write this as a piecewise function. So it's going to equal x squared minus 9 over x minus 3. If x is not going to equal 3, and it's going to be 6 if x equals 3. Okay. So that's how we want to define g of x. Okay, next let's look at a similar problem. We're going to have, well, we want to define h of 2 in a way that extends h of t equals t squared plus 3t minus 10 over t minus 2. And we want to make it continuous at t equals 2. So we want to show, or want this to satisfy, so the limit as t approaches 2 of h of t to equal h of 2. Okay, now h of t is going to be the t squared plus 3t minus 10 over t minus 2. This we can simplify. So we can simplify the numerator as t minus 2, t plus 5, now the factors of t minus 2 are going to cancel, and if I plug in t equals 2, I get 7 as my limit. And we want that to be h of 2. So we're going to define h of 2 to be 7. So we can, if we choose to, write a piecewise function. We can let it be t squared plus 3t minus 10 over t minus 2 when t is not equal to 2, and 7 if t equals 2. Okay, next, let's look at, so we want to define f of 1 in a way that extends f of s equals s cubed minus 1 over s squared minus 1. So this has to be continuous at s equals 1. So we want to set this equality equal. So we'll say limit as s approaches 1 of f of s has to equal f of 1. Now f of s is s cubed minus 1 over s squared minus 1. And here we can simplify. So s cubed minus 1, we can think of s cubed as s times s, and 1 as 1 times 1 times 1. And here we're going to use the SOAP method. So the way it works is in the first parentheses, we're going to choose one of the factors here. So the s and the 1. And then the other parentheses, we're going to group them. So we're going to pick 2 at a time. So s times s, s squared. S times 1 is 1s. 1 times 1 is 1. And finally, we're going to use the SOAP method. So the S stands for same. So here, the sign is minus. So we're going to keep it the same sign. O is opposite. So the opposite of minus is plus. And then AP is always positive. So we're going to keep that as plus. And then in front, we're going to have the limit as s approaches 1. And in the denominator, we also want to factor s squared minus 1. So we're going to have s minus 1 times s plus 1. The s minus 1 factors are going to cancel. And now I'm just going to plug in s equals 1. So in the top, I'm going to get 3, and in the bottom, I'm going to get 2. So we want this to equal f of 1. So we're going to define f of s to be s cubed minus 1 over s squared minus 1 if s is not equal to 1. And we're going to set equal to 3 halves when s is equal to 1. And then now this piecewise function is going to be continuous at s equals 1. Okay. Now let's look at another function. So we're going to have, so we want to define g of x, or g of 4 rather, in a way that extends g of x equals to x squared minus 16 over x squared minus 3x minus 4 to be continuous at at x equals 4. So by definition, we want the limit as x approaches 4 of g of x to equal g of 4. Okay, now g of x is x squared minus 16 over x squared minus 3x minus 4. Here we can factor both the numerator and the denominator. So the numerator is just a difference of 2 squares. And then the denominator we can factor into x minus 4, x plus 1. The x minus 4 factors are going to cancel. And if I plug in x equals 4, I get 8 at the top and 5 at the bottom. So my limit as x approaches 4 is going to be 8/5. And that's going to be what I want g of 4 to be. So we're going to define g of x to be x squared minus 16 over x squared minus 3x minus 4 whenever x is not equal to 4, and 8/5 when x is equal to 4. And this function now is going to be continuous at x equals 4. Okay. Next, we're going to be looking at finding values to make the piecewise function continuous. So let's say we have f of x to be x squared minus 1 if x is less than 3, and 2ax if x is greater than or equal to 3. So we know by themselves x squared minus 1 is continuous everywhere, and 2ax is always continuous. But the problem is at x equals 3. So if we were to graph this, just to get an idea, to the left of 3 is going to be x squared minus 1. So something like this. And here let's see. If I plug in x equals 1, if I plug in x equals 3, I get 8. Okay. And then to the right is going to be a linear function. So it depends on the value of a. So a could be negative, which will make this line be negative, which that doesn't make sense because it would fail the vertical line test, right? This is not a function. So that can't be possible. So basically what we want is a to be positive and to connect over here. So I wanted to fill this hole and then to go on from there. So that means that the left-hand limit, so as we're approaching 3 from the left, from x squared minus 1, that limit has to be the same as approaching 2ax from the right at x equals 3. So what we want to do is we want the limit as x approaches 3 of x squared minus 1 to equal the limit as x approaches 3 of 2ax. Now on the left-hand limit, here I'll plug in 3 and I get 8, just like what I have here. And if I plug in 3 for 2ax, I get 6a. I divide by 6, and I simplify, and I get a equals 4/3. So when a is equal to 4/3, my function now is continuous at x equals 3. So not only is f of 3 equal to 8, but it's also the limit as x approaches 3 of f of x. And that, because it satisfies this equality, it makes it continuous.